So hi, in the previous video we talked about the independent operation of synchronous generators, and today we will continue with the operating modes. But let's do a quick review. So this is again the full equivalent circuit, and we can control the field current to control the magnitude of EF, and depending on your output voltage, then you have some current, also magnitude, and the power factor is determined with respect to load or with respect to the difference between EF and V. Okay, so if you have like independent operation or standalone operation in a generator, so basically there is nothing that holds the terminal voltage, that is completely variable. And what you are doing is, if you don't have any field control, so EA magnitude will be constant, so depending on the load, so the output voltage will be changing. And we have already discussed the effects of a lagging power factor, like unity power factor, or in leading power factor it can even like increase. As you increase the load, the output voltage can go up. So the idea is to have some kind of control loops to ensure that you have constant frequency and constant voltage magnitude. So there were like two independent control loops. One of them is controlling the output voltage by adjusting the field current, and that is the AVR, automatic voltage regulator. And the second one is like controlling the mechanical input power by injecting more fuel or opening up the hydroelectric power lamps, that kind of things. And that is done by a speed governor, by a speed controller. So today we will talk about what happens if you don't have just a single generator, but if you have many synchronous generators connected in parallel. So here, that's the usual case, and here you have seen like you can see like three generators connected to the same bus, and they are supplying a single load, or again there can be like many loads connected in parallel on the load side as well. And actually, if you think about it, that is what's happening in every countries. We have like many generators connected in parallel. Actually, this is a hydroelectric power station, so you can see like many generators, they are connected to the same bus. Actually, it is not only about those generators. All of the synchronous generators in Turkey, they are all connected to each other. They are all rotating at the same synchronous speed. They are all supplying power to our cities, and it's even not only our country. Turkey is also connected to European system through Greece power grid. So basically all different countries are connected to the same AC system if their voltage and frequencies are same, and the generators they are all rotating at the same speed like that system. And this is the interconnected system, and like this is operated, and like the main control room actually in Ankara, in Gölbaşı. I don't know if you had chance to visit Emir Lake. Probably you have seen the Teyyaş control station, which they all coordinate, like which generator is going to generate how much power. And actually, if you are interested more about these topics, you can choose the power systems area in your fourth year. Anyway, so what happens? Okay, that is our condition. So let's say you have one generator, or maybe many generators already connected, and they are already running. And what you want to do is you want to connect another generator to the same system. Maybe the load increase, and this generator is already generating its maximum power. So you need to introduce some generators to the system, and you have to do through that kind of connection. So what are the conditions for closing the switch? You cannot just close the switch immediately. Maybe the voltages are different, and that will induce like really large current. So before closing the switch, and you just excite that generator, and that one is already rotating. Maybe you turn on diesel generator, maybe again it's a thermal power plant, you burn some coal or natural gas to generate some heat, then heat produces some steam, and then steam started rotating the generator, and you want to ensure that the voltages and frequencies should be equal to each other before closing that switch. So we will discuss that one. So first you want to make sure they have equal terminal voltage, so there shouldn't be like any high inrush currents because of voltage difference. So the voltage at that side should be equal to voltage at that side, and moreover the frequency should be same. So even if like both of the generators are generating 230 volts, if one of them is rotating at 40 Hz and the other one is rotating at 50 Hz, then they will introduce again some inrush currents between those terminals, which can damage your system or also generators. Also, you want to make sure there is no phase difference. They can have the same voltage and frequency, but if there is some phase difference between those ones, then there will be some large currents flowing between these two terminals. Okay, and also you want to make sure again they can be all same, but one of the generators can be connected like ABC, ABC. The other one can be connected like ACB, ACB, like phase sequence can be different. So you need to make sure those are same. Unfortunately, we will not be making any labs this semester, but I think this was the synchronizing some generator to the grid was quite interesting, and it was challenging labs in this semester. So like, can you propose a very simple method to check all these? So we want to make sure in any condition there is no voltage difference between these two terminals. Okay, again I will show a couple of videos. There are some sophisticated methods, but the simplest method would be just connect a light bulb from here to here. So whenever there's a voltage difference, okay, so you can connect a lamp here. So whenever there's some voltage difference, you will see those lamps are on. But if the voltage on that node and that node are same for some time, then all three lamps will be off. Then that means there's no voltage difference, and then you can close your switch safely. I will show a couple of videos now. So again, you can click on those links. So let's have a look at that one. So that guy is trying to synchronize a hydroelectric power plant to the grid. So let's have a look at the procedure here.
So here's an important thing. Unless we're going to die, don't break away the shop.
So it's a hydroelectric power plant. So he's opening the flaps, and some water is rushing through the turbine and start rotating the generator. Okay, so now you have some water coming in through the gates. You can see the water current. Okay, then here you see the frequency, then that frequency will start going up. So now it will go up, and those two lamps, okay, those two lamps are the lamps that I was talking. So those lamps are the lamps here. I think they didn't put a third one, because if two of them are off, the other one in a balance system will be off. So they have just two systems, but whenever there is that bulbs are on, that means there's some voltage difference. Okay. So here this is your frequency of the generators, and now you start, I think, generating. So now that one is that is US, so it has to be like 60 Hertz. So this is the 60 Hertz graph, and now it is around 57 Hertz, and these are the lights, and there will be, you know, on and off. And that is an arrow that shows if you need to accelerate your generator or decelerate your generator.
Coming through 57.
So look at the light bulbs, they are all, you know, on and off.
Just ease it in there. Come back. You'll get there. Come on, girl.
Anyway, just
Come on.
trying to adjust.
The hole, and that's going to move all the way across the tub until
So
everything-
again, the light bulbs are, you know, turning on and off, because if you have, like, I don't know if it is 59 hertz or something like that, if you have 59 hertz at one side and 60 hertz at the other side, the difference will be around 1 hertz, so the lights will be going on and off at a lower frequency. Okay, if the speed difference increases, they will flash faster.
evens out. So I need to just ride this wave. I'm basically surfing a power plant on a river, and the only control I have is this little switch that opens and closes the valves. So we're just going to let this swing and balance out, but we're going to get there. You just got to be patient. You can't rush.
Again, I think the time constant of the generator is not, you know, so quick, so it takes some time to increase speed, or if it is fast, then it takes some time to decelerate it. But look at the frequency of those lights as it gets faster and faster.
Very big, expensive, angry sounds, because that giant turbine right behind me will synchronize to the grid. No matter when I throw the switch. So if I throw the switch wrong, it's going to hurt really bad.
So it doesn't want to. So you want to make sure, you know, everything is correct before synchronizing.
We're getting better. I'm going to give it just a kiss. And just that tiniest flick of the wrist is all it needs.
Look at the frequency of the lamps. Now you are getting closer to 60 hertz, and they will flash slower and slower. And when they are both off for a long time, that means it is at the same frequency and same voltage.
Now we are very nearly there. We are very, very nearly there. I'm going to come down.
Coming there. Oh, it's now faster. So that arrow shows you to slow down or to increase the speed. So now both of the lamps are off.
Almost. Now I gotta watch this. That was too quick. I'm gonna let this do it nice and slow.
Now it's losing it. It's losing it. But now,
We got it.
so now
That was too quick. I'm
Look
gonna
at
let
that.
this do it nice and slow. But you just
now it's there, and then it closed the switch. Okay, so once you close the switch, now the lamps will be off, and your generator will be rotating at synchronous speed.
we give her what for. We give her all the wicket. We are generating power now. You can see our kilowatts coming up. And you gotta do it quick. You gotta do it quick, because if you don't, you'll fall off the grid. You only get a couple seconds. We're good. Now I'm gonna go to automatic control on my
So now it's switching to automatic control.
the autopilot. The system is now on the grid, and we are beautiful. And we have just turned on a entire 350,000 watt hydroelectric.
So it's 350 kilowatts, I think.
And I want to thank you for your help, and I want to thank Bootsy Armstrong.
Anyway, so again, you know, this is the simplest one. So let's have a look at how it is done in a larger system. So this is a coal power plant in a large system. So they are trying to generate some heat, and then, you know, generate some steam, then rotate the generators, and then they will synchronize. It is much larger than the previous one, and again, you can see the guys are really professional here.
Crews have dedicated a lot of time and energy preparing for major milestones
Put
like
the
this
captions.
one. It's all part of getting the plant.
So here it is like the steam, you know, engines, and you have the synchronous generators here, and that steam is coming from some furnaces somewhere else.
That's the emergency trip system, which is the auto voltage regulator.
The auto voltage regulator is what controls
Like
the voltage
auto
of the
voltage
generator,
regulator,
how the plant actually
AVR. This talking about the AVR.
syncs to the grid.
And then we did a dummy synchronization. What we did is we left the disconnects, the line side disconnects open on the generator breaker.
So let's have a look at those.
The actual sync.
So here you see the turbine speed, unit load, you know, all kind of shafts, bearings, temperatures. So it's more
360
critical
RPM.
system. Now it's being increased. It's again a 60 Hz system, US system. So it's a probably two-pole generator rotating at 3,600 RPM, and they are, you know, disengaged. I think they will just synchronize it with the steam and turbine.
With the click of a mouse.
So they are just clicking on the auto synchronization, and you have the switch here, and they are checking the voltage okay, frequency okay, then it will just close the switch.
Electricity
So
is
it's all
released
done
to the
by
transmission grid.
computer algorithms.
Even Mother Nature has
Okay,
At about 0900.
so here it is generating some power, and again don't forget, you know, at the end of the day, in this case you are burning some fuel. This is a coal power plant. You are burning some coal power plant to send this
propane is
thing.
pulled out and the coal is
Okay, so you can, you know, watch it yourselves to better understand. And this thing, okay, this thing is called synchronous generator connected to infinite bus. So infinite bus is a term you will hear a lot in power engineering area, and that is, you know, of course not that kind of bus or metro bus like one of the ones in Istanbul, but infinite bus by definition is an electric source. Okay, it's electric source so large, so it is that side, okay, that the voltage and frequency assumed to be constant independent of power flow. So you have like maybe hundreds of thousands, maybe thousands of generators on that side. So that defines the all electricity grid of Turkey. So all, you know, like really large generators, and maybe your generator is like the one like that guy connected. Okay, again, it is not a really small system, but you know, compared to your power, actually the power of the grid is so high, so even if you send some power or get some power from it, the speed is not going to change. So you can think that system at the end of the day, it is like a like a rotational system, and you have the kinetic energy like 1/2 j omega square, and you have, let's say, infinite or so large that you can assume infinite inertia that you will not have any control. So once you get connected to your bus, you know, that voltage over here, again, this is your it can be your generator's equivalent resistance and phase, or the power connection that connects your generator, but that part, that terminal voltage will be constant. That wasn't the case in standalone operation, because in the standalone operation we can, you know, even if you changed your load, if you don't modify your field current, then output voltage is going to change. But once you connect it to the infinite bus, that terminal voltage is going to stay. So what happens, for example, if you have a hydroelectric power station, and if you cut off the water, and if you are still connected to that one, and if you don't send enough power through mechanical power through the generator, then your system becomes a motor, so it will start rotating it. So, or if you have a wind turbine, again, you know, most of the wind turbines are nowadays controlled by power electronics converters in between, so it doesn't have to be exactly at the grid frequency, but there are some early examples which you connect the generator directly to the grid. So in this case, if you connect it to the grid, and if you stay connected to the grid even if there is no wind, then your wind turbine starts working as a fan, so it's blowing air, so all that system starts working as a motor. So let's have a look at how does it work. So that is the operation that we have. So this is the three-phase model, and this is our synchronization switch, and on the right hand side you have the infinite bus or infinite bus bars, and the voltage and the frequency of the right hand side will be constant, so you can control the field current to control the EF, but you don't have any control on the terminal voltage. So it will be the synchronous generator connected to infinite bus. Even if you are supplying power, working as a generator, or if you are consuming power, the frequency will stay at 60 Hz. Of course, there are some, by the way, automatic circuit breakers. If the currents are getting too high, it can automatically disconnect it from the grid. You can control that kind of reverse power flows. But if you just connect your synchronous machine to the grid, so it will rotate at that speed. Okay, and again, regardless of how much reactive power that you are supplying or consuming, we will discuss those things, the output voltage will stay constant, because in the previous case, depending on your lagging power factor, leading power factor, your output and your terminal voltage is changing, but not in a generator connected to infinite bus. Okay, so you can write the equation. It is still like that. So EF, if it is working as a generator, VT plus RA plus JXS times IA, nothing different that we did. The direction is minus for motoring and plus for generating, but the thing is now VT, that term is constant. Okay, you cannot change that one. So if that one is not changed, depending on the magnitude and phase of EF, so now the current is a direct output of these two parameters. That is constant, that is what you can control, and that is your output results. Okay, so again, for now, let's ignore armature resistance, and let's have a look at the phasor diagrams. Okay, in that phasor diagram, it's also called like the constant. First, let's say you have constant excitation and variable load, and it's called circle diagram. So here we are looking at the case with the constant excitation, okay, or constant IF. So that means the EF magnitude will be constant. So here again it is working like that form. Again, let's assume it is working as a generator for now. So if it is working as a generator, we can write like EF is equal VT plus JXS IA. So anyway, here again it is connected to infinite bus. That means VT is constant, right? So whatever you do, okay, whatever you do, you will not be able to change the magnitude or the phase of that terminal voltage. So this is infinite bus, and it will stay there whatever you do with your field current. Okay, so I know if it is working at the constant excitation mode, then EF magnitude, let's use the same colors, so EF, let's say here, right, and EF magnitude is constant. So you have that point constant, and that one, okay, can only move along that circle, okay, because the magnitude is going to be constant, and you have your load angle. If you are increasing your power, okay, if you are increasing your power, it will move on. I mean, let me write increasing mechanical input power to your generator, power, or if you can go that way, decreasing mechanical power. Okay, so by sending more water to your turbines, sending more fuel to your diesel generator, you can actually control the torque and you can control the load angle, and the resultant part is going to be the difference. So that has to be, again, in order to have that waveform, so as a result of your mechanical input power and IF excitation, so you will have the voltage drop on JXSIA as a result, okay, as a result of IF and P. So if you have that kind of waveform, then you can again have the same current, and that will be some current, and this is your power factor. And you can see by moving the power up and down, actually you can have that thing is going to be up and down with increasing power if it moves like that. Let me draw a secondary case. Let me draw another one. For example, if I have that one, and let's say I increased the power quite a lot, and now my power factor is increased along that circle again. I don't know if the so now that one is larger than that one by increasing mechanical power, and as a result I will have that kind of thing. And again you can see my power factor. Okay, my power factor, I don't know if it will be, probably it will, I think, or let me adjust it to be exactly unit power factor. Somewhere here, right? So it will be like that, and my IA will be like that. So again, if you increase mechanical input power, it will come like that. It doesn't have to be unity power factor, I just draw it like that. So here again, increasing power. Okay, so that is called the constant excitation mode. So IF magnitude constant, or if you have that kind of graphs, so mathematically VT, that is constant, you can control EF, and EF can be constant, so you can subtract these two and find the amount of current that is going to flow through the machine. So here we have an animation. Let's have a look at that one. So I think it will help you to understand better. Okay, zoom out a little bit. So here that is my constant E, and that is my circle curve. And I can increase power. Okay, power is the input power, and you can see all those numbers. So I am increasing, or let's decrease at first. So I have no power at first, and the current is like flowing at 90 degrees. So it's purely reactive power, no real power. And I start increasing the power. I keep increasing the load angle. Okay. So now I think this animation was up to here. Then what I can do is I can control, for example, for a given angle, given power factor, I can increase my field current, which it will increase the E, okay, or I can decrease it, and again by decreasing it I can, for example, for the same power, okay, for the same power I can control the field current to adjust the power factor, you see. So I can operate my generator. There's a point which can operate at unity power factor, or I can apply more field current which will operate in the lagging power factor, or I can operate at as a leading power factor. Or for the constant V, if I change the power, then all that thing is moving up and down. Please, play it yourself and have a look at the numbers, and then you will have a better understanding. So the second operation mode is the constant power with changing the excitation, and actually I already showed the animations for that. To discuss that one, let's remember what was the power in an AC system. Real power is again terminal voltage, phase current, power factor times 3. 3 is coming from the 3 phases. Remember, all that equivalent circuit is for one phase. So let's have a look at what is that equals to. You can say, in that operation mode, like P, if P is constant, again, like keeping P is constant means you don't change the amount of water rushing through your hydroelectric power plant. There's a net mechanical input power, and your terminal voltage is constant because that is which you cannot change, that is the infinite bus. So if that one is constant and if that one is constant, so that means the power factor, the magnitude of IA times cos theta should be constant. And what is that equals to? So okay, here I draw the same phasor diagram. So what we already said is like it is Vt times Ia times cos theta. So that is the power, power coming out of the turbine, out of the generator. It is 3 times Vt times Ia cos theta. And what we say, if Vt and P are constant, okay, if they are constant, I can say Ia cos theta is constant. Okay, so I can write Ia cos theta is constant. So what is that thing equals to from geometry? Right. So let's try to get that distance, right? So that distance over here, what is that one? If I just plot here, if this is delta, this is 90 minus delta, this is 90 degrees, this is 90 minus delta, and this is that angle is delta over here, right? So if this part is delta, that curve is xs magnitude wise, it is xs times Ia times cos theta, right? So that yellow area is equal to that angle. But also I can represent it from here, right? So if this is EF magnitude, I'm talking about the magnitudes here, that angle is also, you can write it the same angle over here using that one. So this is EF times sine delta. So I can say, okay, I will use that equation in the upcoming weeks as well. So I can write EF magnitude times sine delta. This is just from geometry through here. It is XS IA cos theta. And if that one is constant, I can say IA times cos theta is equal to EF times sine delta divided by XS. Is going to be constant, and actually XS is a machine parameter, so it's not going to change. So actually that distance is going to stay constant. So during constant power operation, you can just move, okay, having that one constant means that green arrow can only move along that horizontal line. It will just move along that horizontal line. Actually, that is what you were seeing in the previous slide if you didn't realize. So that one is constant. So from geometry I can say EF sine delta is equal to constant. And let's look at the same animation. Okay, so if I don't change the power, okay, so it is working at constant power, and if I just play with the field current to change the magnitude, let's just have a look at the green arrow. So it is just moving along that line if I'm not changing power but increasing field current. And if I am changing the power, then that green arrow is just coming up and down. Okay, so that one is going up and down by changing power, or you can increase EF and then you are moving along the horizontal line. So once you get connected to the infinite bus, you have like two control modes. You don't have any control on the speed and the terminal voltage, but you can change the power or you can change the field current to change the magnitude of EF. So we will use those terms to derive the power and torque equations of a synchronous machine. But please do a couple of exercises, and I'm planning to solve a couple of numeric solutions in the following lectures. So hopefully it will become clear. Okay, thank you.